On October 3rd, 2025, an interstellar visitor known as 3I/Atlas will zip perilously near Mars, marking the inaugural real-world trial for all operational probes and landers against an extraterrestrial hazard, just as our planet dips into a solar shadow, severing all sight lines. Experts anticipated a routine skim past. What they encountered was a comet thrumming with CO2 emissions, flaring unpredictably in luminosity, and defying every norm of solar system dynamics. Government predictions gloss over the communication blackout, the wild intensity spikes, and the fallout from abruptly losing contact with Mars satellites. So, what's the true potential of 3I/Atlas to disrupt Mars in its most dire moments? The most alarming outcome might not involve a collision, but rather the unforeseen chaos unfolding during those blind hours when oversight fails. This date in 2025 transcends a mere entry in mission logs. For the first time ever, a body originating from beyond our star system will traverse the vicinity of the red planet amid a bustling array of circling spacecraft and surface explorers. There's zero practice run for such an event. No historical parallel exists. Each satellite orbiting the planet and each automaton traversing its terrain now participates in an unscripted trial of cosmic safeguarding. The scale of this is mind-boggling. 3I/Atlas will sweep by at approximately 30 million kilometers from Mars, equivalent to about 75 times the Earth-Moon separation. That distance may seem vast, yet in cosmic measurements, it's alarmingly narrow, particularly for something hurtling at close to 68 kilometers per second. The red planet has never hosted an interstellar interloper this near, much less with such extensive equipment at risk. Adding to the gravity of the moment is the impending communications void. As 3I/Atlas draws nearer, Mars will align behind the Sun from our vantage point on Earth. Over a span exceeding 1 month, mission operators will navigate without visual or data feeds, powerless to act if crises emerge. The risks extend far beyond hypotheticals. They're quantified in billions of dollars invested, years of pioneering voyages, and the endurance of humanity's inaugural off-Earth observatory web. October 3rd transforms the vague peril of interstellar wanderers into an undeniable, unchangeable challenge. As the third verified interstellar body to enter our solar system, Atlas shuns conventional comet patterns. Initially, it resembles a grimy ice ball on a hyperbolic path, racing by Mars at nearly 68 kilometers per second, a pace swift enough to traverse the width of the continental U.S. in less than a minute. Yet, deeper scrutiny reveals escalating oddities. Its minimal distance, ranging from 0.19 to 0.20 astronomical units, or about 30 million kilometers to Mars, positions it firmly in the local zone, near enough for Martian satellites to snag imagery invisible from terrestrial scopes. The standout features go beyond mere speed or trajectory. It's the composition that captivates. Atlas exhibits a surrounding haze dominated by carbon dioxide rather than water vapor. Typically, comets rely on H2O ice as their primary driver. Here, though, CO2 venting eclipses all other elements. This disproportionate makeup compels astronomers to reassess possibilities in extraterrestrial compositions. Compounding the intrigue are the luminosity fluctuations, unpredictable, at times ferocious bursts that intensify and dim abruptly. The patterns of ejected material defy simulations. Streams erupt in bizarre directions, while the whole sheath appears to throb with internal force, as though an inner force strains for release. To those studying worlds, Atlas functions more as an enigma than a guest. Its capricious actions, foreign makeup, and velocity all provoke a shared disquiet. What secrets lurk within this enigma? And what reactions might Mars unleash as it enters the direct line of sight? Between October 1st and November 9th, 2025, both Mars and 3I/Atlas will retreat into an observational dead zone, positioned under 30 degrees from the Sun as viewed from Earth. For those directing operations, this translates to over a month of disrupted transmissions, with every message battling through the Sun's overwhelming glare. No surface-based observatory, no far-reaching radio array, not even the James Webb or Hubble, can monitor the comet's nearest pass. The remaining observers are the probes encircling Mars: MAVEN, MRO, TGO, Mars Express, and Tian-1. These vessels turn into the exclusive recorders, transmitting sporadic updates through a data chasm that might engulf everything from a subtle flare-up to a devastating incident. This isolation goes beyond mere hassle. It exposes a critical weakness. Should Atlas shatter, intensify, or exhibit unprecedented antics, our world would remain in the dark during the action. Teams of technicians have drilled emergency protocols for years, but with the alignment period approaching, each possibility turns into a gamble. In the nerve centers, crews brace for the chance that pivotal breakthroughs or calamities will unfold unseen, leaving only the weakest digital traces to pierce the interference. Picture a metropolis-scale relic from a distant stellar realm surging toward Mars and abruptly disintegrating at interstellar velocities. That's the prospect haunting specialists at ESA and JPL through sleepless nights. When a comet such as 3I/Atlas shatters in proximity to a world, it doesn't simply dissolve. It scatters the surrounding orbital space with a cluster of defragments. From such a breakup can linger for years, sometimes even decades. Every piece, whether massive boulder-like slabs or swirling dust plumes, charts its independent trajectory. Certain bits skim Mars' upper atmosphere, while others get temporarily ensnared in orbits around the world. What emerges isn't one isolated incident, but a dynamic hazard zone in constant flux. Simulations indicate that even a modest disintegration might disperse thousands of shards, from tiny metal-like flecks to enormous chunks spanning hundreds of meters. A portion of them succumb to Mars' gravitational pull, tracing erratic paths that eventually lead to atmospheric entry or a forceful ejection. Additional debris might intersect with the routes of Phobos and Deimos, the red planet's delicate satellites, or hover in the busy pathways frequented by probes. Every orbital sweep heightens the chance of a smash-up, not merely now, but for all subsequent ventures navigating this perilous maze. The danger extends far beyond any one period. These debris fields can morph, break apart more, and generate fresh perils with each Martian cycle. The ESA's ENIO Coordination Center cautions that the gravest scenario isn't a flashy collision, but a gradual chain reaction, resembling a Kessler syndrome ring of wreckage that could transform Mars' orbital space from an entry point into a lethal trap. For the planet itself and every probe or human explorer that comes after, the remnants of a shattered cosmic wanderer might be gauged not by fresh pits, but by the unseen, enduring peril of debris floating amid the crimson world's atmosphere. A fragment the size of a city block from 1I/Oumuamua, slamming into Mars at 68 kilometers per second, would release energy surpassing the combined output of Earth's global nuclear stockpiles. The scale is tough to fathom. A 1-kilometer core hurtling at that speed packs sufficient force to carve out a basin reaching 35 kilometers in diameter, an orbital landmark enduring for eons. The blast pressure wave would melt stone into vapor, instantly scorch the terrain, and loft billions of tons of pulverized soil into the sparse Martian skies. Ground-based machines like Perseverance, Curiosity, and Zhurong have nowhere to hide. A suffocating veil of grit would cascade down, smothering photovoltaic arrays, jamming intakes, and casting the landscape into shadow. Even those fueled by atomic reactors would falter as daylight fades and chills deepen. Yet the chaos wouldn't confine itself to the strike site. The detonation would loft ultrafine particles and vapors aloft, diffusing rays and inducing a global twilight. For weeks, perhaps seasons, Mars might endure a simulated frost era, cooling air, halved illumination, and a terrain veiled in rusty mist. Satellites circling above would confront their separate ordeal. The impact's electromagnetic burst, intensified by turbulent electrified particles, might disrupt instruments, activate shutdowns, and sever links. Teams back on Earth, already hampered by solar alignment blackouts, could remain unaware for days whether their vessels endured. In mission hubs, each vanished transmission would hit like a visceral blow, underscoring that Mars has become a proving ground for catastrophe. The aftermath hinges on whatever infrastructure survives the fallout. Unseen dangers may spare the terrain from marks, yet they can disrupt a world's whole electronic framework. As One-Eye/Oumuamua glides by Mars, it hauls along an immense shroud of charged vapor and grit, an energized plasma weave, right across the Martian domain. Unlike Earth, Mars lacks robust defenses. Its fragile air layer and fragmented magnetic remnants in the crust render it highly susceptible to electrodynamic disruptions. Experts monitoring cosmic storms understand the fallout when a comet's charged envelope grazes a world. In 2014, comet sighting springs sparked widespread auroral displays on Mars, fleeting spectral veils of UV glow far more vivid than prior observations. But One-Eye/Oumuamua stands apart. Its envelope brims with carbon dioxide, set to unleash ionized bits at levels unprecedented for Mars satellites. In the close approach, the ionosphere might swell dramatically, igniting vast auroral sheets across the globe and saturating the upper air with energetic electrons. This goes beyond mere spectacle. Spikes in atmospheric charge could overwhelm probe detectors, engage error safeguards, and disable signal networks. Odd magnetic zones in the southern uplands function as boosters, channeling electric flows and birthing pockets of intense charge activity. Planners fret over bit flip incidents, subtle, undetectable zaps that might corrupt data storage, derail guidance, or compel a satellite into emergency standby without notice. Even absent any direct fragment strike on Mars, the electrodynamic ripples from One-Eye/Oumuamua could cascade across all orbital assets. For operators, the true menace might be the sort that scars nothing visibly, yet temporarily silences the whole armada around the rusty orb. Safeguard specialists have long geared up for microbial uncertainties, but no protocol addresses a wayfarer from afar infused with extraterrestrial compounds. As One-Eye/Oumuamua hurtles by Mars, its CO2-laden envelope isn't merely an oddity in composition. It serves as a carrier for intricate carbon-based substances, potentially including pseudo-organic materials. Should pieces or particles from the comet plunge into Mars's atmosphere or land on its terrain, subsequent biosignature studies will confront a fresh challenge, distinguishing indigenous Martian biology from extraterrestrial pollutants. Just a smattering of carbon-laden specks might obscure the boundary between local reactions and alien interference, transforming the quest for life into a prolonged argument about misleading signals. Yet the repercussions extend beyond lab equipment and analyzers. Should substantial chunks collide with Phobos, the closest satellite to Mars, the effects might escalate to a global magnitude. Phobos is pockmarked with cracks and scarcely maintains cohesion against gravitational stresses. An onslaught of comet rubble could hasten its disintegration, hurling debris into space and generating a short-lived ring encircling the red planet. For satellites and upcoming expeditions, this represents more than a routing obstacle. It's a dynamic gauntlet featuring chunks capable of damaging probes or sparking chain reaction impacts. In the grimmest scenario, Mars might acquire a ring in mere hours and forfeit secure airspace for an extended period. Not all remnants of 3I/Atlas will linger near Mars. Certain ones, propelled by the subtle yet persistent pressure of solar radiation, known as the Yarkovsky effect, embark on a gradual migration, their trajectories elongating and altering across years. For experts in celestial safeguards, this unfolds as a creeping catastrophe. Material that evades prompt identification then stealthily relocates, occasionally veering toward Earth's orbital zone. Gravitational harmonies with Mars or Jupiter might intensify such movements, redirecting particles onto trajectories that intersect planned probes or, infrequently, our own world. The vast majority pose no proximity threat, yet a slim probability, say, 1 in 1,000 across 100 years, suffices to unsettle hazard evaluators. These objects evade easy spotting. Their heat signatures, uneven forms, and erratic rotations render them tougher to monitor than standard space rocks. Sensors designed for ordinary dangers could overlook a building-sized artifact from beyond our system, somersaulting through an unanticipated orbital plane. Thus, the aftermath of 3I/Atlas transcends mere disruption at Mars. It's an enduring narrative of ambiguity spanning eras, with Earth as a conceivable, if improbable, destination. Mars embodies a fragile equilibrium, with its sparse air, iron oxide soil, and sufficient solar warmth to prevent total surface icing. When an extrasolar visitor like 3I/Atlas hurtles by, trailing a hazy envelope loaded with CO2 and shadowy particles, a mere close pass can disrupt that poise. An abrupt influx of CO2 and minuscule grains doesn't merely obscure the heavens. It alters the amount of light hitting the surface, modifying the planet's albedo, its light-bouncing capacity, by percentages critical to weather simulations and ground operations. A shaded Mars chills swiftly, whereas added CO2 might disrupt rover energy calculations and long-term strategies for tapping local resources. However, the tangible debris isn't the sole wave of impact. As the world dips behind the sun, conjecture surges ahead of evidence. Online platforms brim with theories, accidental world building, concealed strikes, outright deceptions. Coordinators of missions and guardians of planetary hygiene must contend not only with grit, but with preserving truth amid rampant myths. Ultimately, the gravest danger could lie in those shadows-fueled tales, which erode confidence in science and steer the course of Martian ventures well after the particles descend. In late October 2025, celestial dynamics converged dramatically. 3I/Atlas hits its closest solar approach at 1.36 Australian dollars precisely as solar cycle 25 peaks near its zenith. Forecasters of space climate prepare for heightened solar outbursts. Prominences from the corona, blasts of high-energy particles, and propagating shocks that can unsettle the sunward solar realm. Amid solar maximum, the star unleashes 4 to 6 significant flares weekly, with solar wind velocities exceeding 1,000 kilometers per second. Layer on an extrasolar comet brimming with CO2, its expansive ionized tail unfurling, and perils multiply. Should a solar flare batter Atlas's envelope with Mars caught in between, the ensuing magnetic chaos could surpass prior Comet Mars brushes. For the array of satellites and surface craft, this brews an ideal tempest. Overlapping dangers, erratic ionized streams, and a communication void when monitoring tools already teeter under load. Projections of equipment losses sketch a grim vista. If shards from 3I/Atlas or one of its urban-scale nuclei impact Mars, the outcomes develop gradually, yet inexorably. Plumes of dust lofted aloft would have incoming sunlight, plunging ground temps by up to 20 degrees Celsius for months or longer. Sun-reliant vehicles stall amid a dense reddish veil. Satellites forfeit starbase navigation, then drop off the grid. As electromagnetic pulses ripple through the ionosphere, telemetry signals from spacecraft begin to falter. In mere weeks, control centers hear nothing back from nearly half the orbiting probes. The damage extends far beyond mere equipment. It's the vanishing of years' worth of Mars weather records, biological marker tests, and the sole reliable views of the Crimson World. For those handling mission hazards, the gravest threat isn't one isolated strike. Rather, it's a prolonged dark period, a total shutdown across the planet, and the irreversible wipeout of an era's achievements in space discovery. In this era of cosmic dangers, being ready involves far more than scanning the heavens. It requires innovative safeguards for our world that operate independently amid communication blackouts. Following the trio of I/Atlas events, organizations like space agencies and private watchposts are advocating for a robust alert network covering Earth alone, but extending to Mars, its satellites, and the pathways connecting them. The takeaway is unmistakable. Any blind spot in surveillance represents a weakness, and each lag in information flow can escalate guesses into widespread alarm. Continuous monitoring of signals, surges in electromagnetism, alterations in light spectra, and haze in the dust layers forms the core of such vigilance. Advocacy for shared datasets intensifies as researchers contend that openness serves as the strongest counter to misinformation. Amid uncertainties from the cosmos, the immediate focus shifts beyond merely identifying another Atlas-like intruder. It's about crafting infrastructure that detects the faint, the quiet, and the unusual threats well before they upend the guidelines for venturing to distant realms. On October 3, 2025, 3I/Atlas will streak by at a distance of 0. 19 to 0.20 astronomical units from Mars. This encounter represents the inaugural instance of an extrasolar visitor approaching so near a body, hosting operational robotic outposts, highlighting the distinct hurdles in safeguarding planets. Observations indicate that 32/Atlas deviates from standard comet patterns. Its atmosphere rich in carbon dioxide, erratic luminosity, and the shape of its jets disrupt conventional theories. The extended period of solar alignment disruption will postpone vital observations, compelling ground teams on Mars to shoulder the burden of detection. Formal evaluations of collision dangers outline perils from breakup, disruptions to electronics, and enduring risks from scattered remnants. Still, the full scope of shifts in the atmosphere or orbits stays elusive. Undeniably, though, experts in planetary protection and research are swiftly refining their observation setups and contingency plans. Regardless of what transpires during the 32/Atlas approach, it signals a pivotal shift, compelling our solar neighborhood to confront perils originating from afar.